Hello, welcome back. We have been talking about AC circuits, that's alternating current circuits. And we have looked recently at RC circuits with an AC source. And we saw that those RC circuits were able to be very useful because they give us a low pass filter or a high pass filter, depending upon how they are configured. Now we're going to look at what happens if we have an inductor in an AC circuit. And we'll look at RLC circuits. Let's start by looking at an inductor. This figure shows the instantaneous current, little I sub L, through an inductor. So here's our instantaneous current, little I sub L, through our inductor. And we know that when we're talking about the magnitude of an instantaneous inductor voltage, that will be little v sub L equals L times di sub L dt. So if the current is changing, and it's the only time that we will have the voltage across our inductor is if the current is changing, then the instantaneous inductor voltage is V sub L equals L di sub L dt. Now the potential decreases in the direction of the current if the current is increasing, and increases if the current is decreasing. So this is just the magnitude, but it depends on which direction the current is either decreasing or increasing. That will give us whether it's positive or negative. So now we're going to take our figure here where we have a circuit, an AC circuit with an inductor. So the figure shows an inductor L connected across an AC generator of peak EMF right here, equal to V sub L. So that means that the instantaneous inductor voltage right here, little v sub L, is going to be equal to the EMF. So little v sub L will be equal to our peak EMF, which will be big V sub L, cos omega t. So now combining the two previous equations for V sub L, we have the one that we just got, little v sub L equals big V sub L cos omega t. And we have the fact that little v sub L equals L, the inductance, di sub L dt. So I'm going to set these equal to each other because they are equal to each other. And I'm going to rewrite them here. We have L di sub L dt equals v sub L cos omega t. Dividing through by L, this becomes di sub L dt equals v sub L over L times cos omega t. What I notice here is that I have the variable t on the right-hand side, and I have di dt on the left-hand side. So what I want to do is separation of variables, where I separate this derivative into two pieces. And so to do that, I will end up with taking my dt onto the other side of the equation. So di sub L will be equal to v sub L over L cos omega t dt. That's written right here as well. Now what I can do is I can integrate both sides. So integrating both sides, I'm going to integrate this side from 0 to I sub L. And I'm going to integrate, I can go ahead and put that integral after my constants here. And I'm going to integrate this side, just from 0 to t. So here that is rewritten here. I've already gone ahead and taken the left-hand side, the integral to the left-hand side, and I just have little I sub L. And now we can take the integral of cos omega t, and that will just be the integral of cosine is sine, but we have omega t, so we have to do 1 over omega in that case. So we'll have, in that case, v sub L over omega L times sine omega t. Now we want this in terms of cosine, not in terms of sine, so that we can see how the phase is related. So we know that sine omega t, right, sine of x, we have sine of x, that's the same thing. We can rewrite that as cosine of x minus pi over 2 or 90 degrees. So using that, we can rewrite this as the peak v sub L over omega L cos of omega t minus pi over 2. So now we have this in the form that we're looking for, where we see that our instantaneous current, inductor current, is equal to some constant right here times cosine of omega t and some phase shift here minus pi over 2. So this constant right here, this must be equal to our peak current across the inductor, our peak inductor current. And so this we'll then define as our peak inductor current, where I sub L equals VL over omega t is the peak or maximum inductor current. So let's go ahead and plot both our instantaneous inductor current and our instantaneous inductor voltage. So here we have I sub L in purple, and here we have the voltage, the instantaneous voltage V sub L in green. And what we see is that when I sub L right here is 0, V sub L is at a peak, and that right here, when the current, the instantaneous current is peaking, right at that moment, we see that the instantaneous voltage is in fact at 0. So what we see is that an inductor's current and voltage are not in phase. And instead, the current peaks 1/4 of a period after the voltage peaks. So this tells us right here that the current peaks after the voltage peaks, 1/4 of a period after the voltage peaks. And so we see that in this case, the current lags the voltage. So let's go ahead and draw this as a phase diagram, a phasor diagram. So here's our phasor diagram for the inductor circuit. In this case, we have our voltage phasor and our current phasor. And what we see is that our current phasor lags the voltage phasor by 90 degrees or pi over 2 radians. The AC current through an inductor lags the inductor voltage by pi over 2 radians or 90 degrees. Now that's how we can relate. So now that we see that there is that lag between the voltage and the current for an inductor, the next thing we want to do is think about what kind of reactance we can define for an inductor current circuit. So we can define the inductive reactance. We define the inductive reactance, which is analogous to the capacitive reactance, to be X sub L equals omega times L. So in this case, what we see is that the reactance is directly proportional to omega. It's directly proportional to the angular frequency. So the reactance increases with increasing frequency, and it's directly proportional. if we write this in terms of the peak current, we see that the peak current is equal to the peak voltage over the reactance, or that the peak voltage is equal to the peak current times the reactance, times the inductive reactance. So let's now look at what we get when we have an RLC circuit. In this circuit shown, we have a resistor, an inductor, and capacitor. They're all in series. This is called an RLC circuit. So we have R, L, and C all together in series. The instantaneous current of all three elements is the same. So I equals IR equals IL equals IC. And the sum of the instantaneous voltages matches the EMF. So the total EMF equals VR plus VL plus VC. So now what we want to do is use our phasors to analyze an RLC circuit. So here's our circuit. The first thing we're going to do is begin by drawing a current phasor of length I. So here's our current phasor of length I. Now, we see that this is the starting point because the series circuit elements all have the same current I, which we can see right here. They all have the same current I. The angle at which the phasor is drawn is not relevant. Now, the next thing we want to do is to draw the current and voltage, the voltage. And so we see that the current and voltage of a resistor are in phase. So again, we were going to draw the current, the voltage, the resistor voltage, same as the current. So we're going to draw a resistor voltage phasor parallel to the current phasor I. Now the capacitor current leads the capacitor voltage. So in that case, we want to draw the capacitor voltage phasor 90 degrees behind the current phasor. So we're going to draw our capacitor voltage 90 degrees behind the current phasor. The inductor current, on the other hand, lags the voltage. So in this case, you want to draw an inductor voltage phasor that is 90 degrees ahead of the current phasor. Now the instantaneous voltages, satisfy that EMF equals VR plus VL plus VC. This is a vector addition of phasors because the capacitor and the inductor phasors are in opposite directions. Their vector sum has length VL minus VC. Adding the resistor phases at right angles then gives the EMF phasor at angle omega t. The length of the EMF phasor is then EMF naught is the hypotenuse of the triangle. And so EMF naught squared is going to be equal to VR squared plus VL minus VC, the quantity squared. So if VL is less than VC, which we've assumed, then the instantaneous current I lags the EMF by a phase angle, phi. So we can say that the instantaneous current I equals the peak current times cosine of omega t minus v. Based on the right triangle, the square of the peak voltage is then going to be found by doing EMF naught squared equals VR squared plus VL minus VC quantity squared, which is going to be equal to R squared plus X sub L minus X sub C squared. We're going to pull out the I squared like we did before. We wrote each of the peak voltages in terms of the peak current I and a resistance or reactance. consequently, the peak current in the RLC current, we can then, in the RLC circuit, we can then solve for that by just dividing through here by R squared plus XL minus XC quantity squared, and then taking, so that goes away from here, and then taking the square root of both sides. And we end up getting that the peak current is EMF naught over the square root of R squared plus the quantity X sub L minus X sub C squared, which we can rewrite X sub L, we know, is equal to omega times L, and X sub C, we know, is equal to 1 over omega times C. So that's how we can get the peak current in an RLC circuit. Now, sometimes it's also good to get the phase angle. So we know the current lags the EMF by a phase angle phi. It is often useful to know the phase angle between the EMF and the current in the RLC circuit. So in that case, we see that the angle phi is going to be equal to tan to the minus 1 of VL minus VC over VR. And so we can get the, and so then just factoring out our current from those expressions, we can get that down into the equation that tan to the minus 1 of the inductive reactance minus the capacitive reactance divided by the resistance will give us the phase angle between the EMF and the current in the RLC circuit. So this is how we can have an RLC circuit. We have the resistance, the inductance, and the capacitance in a circuit that's an AC circuit. And we can analyze it to find its peak current and its peak EMF.